We're doing power series around a regular singular point. Now, we did power series around an ordinary point, and with an ordinary point, it was fairly straightforward, as whatever that means. But with a singular point, a regular singular point, we like in general, singular points are when your function won't exist, and so it'll be really hard to deal with it. But for a regular singular point, we have a chance at least, and the chance is by multiplying. Let me squeeze in another page here. So Frobenius allowed us to modify our power series. So instead of a power series that looked like our usual power series, and so this power series starts from 0. K is equal to 0, so it starts off with a constant term. So instead of allowing for that, we use something a little bit different, and we use a series solution that's slightly modified with this R. So that allows us the possibility of starting our R with possibly a less than 1 business, so that we can start our X in the denominator, and so we would be able to handle those singular points, those zeros in the denominator, and then this can mimic something like that. So something like this may not necessarily be a power series anymore. And so we want to allow for this sort of case. R can be anything. It could actually even be a complex number, but we won't be dealing with complex numbers in this class. But it can certainly be a negative number, and it could also be a fractional number, in which case, if R is a fraction, then we're definitely not looking at power series, because power series have polynomial powers. And so that's something entirely different, but it's still based on a series. So Frobenius allows us to be able to come up with a series that is almost like a power series with this extra R. So how to find R? It turns out that finding R is can be done one of two ways. One, we can just try to remember the indicial condition. And 2, the way the book does it, they actually use something a little bit different from how I'm doing it. And what they do is they go through the process of setting up your differential equation, and then they find the roots separately. Not separately, but along the way of solving the equation. So for us, what we did was we used that indicial equation formula. So we used the indicial equation formula to come up with our roots, and then from here we're going to solve it. We're going to solve for the roots one by one. All right, so this is where we left off last time. We found the roots for the indicial equation, which is 0 and 7/6. And again, 7/6 is not a whole number, so when you put this into your equation, then it's not technically a power series anymore. But 0 looks like it would be. So I think last time I even included this one extra step, so our solutions would look like this, or y1 solution. Let's say the r is equal to 0 is what we use for y1. Your solution just would be a regular power series like we've seen before. plus 0. I'll put a plus 0 here just so we can make a point of saying that we're using Frobenius. And then y2 would be this strange looking power series with x to the 7/6. Did I record? I'm recording. All right, so let's do this one by one. Now, I think I told you that when we were working on this earlier, when we take derivatives, we shift the index. But because we have this mysterious R business happening, we actually are not going to be shifting indices for when we're doing this Frobenius theorem. Okay, so let's focus on this one for right now. Now we need to find the first and second derivatives of this and put it back into the original differential equation. And what we're going to do is to be able to allow for the R, and this is where it kind of makes more sense the way the book does it than the way I'm doing it. I'm going to keep the index at k is equal to 0. Oops, I need to take the derivative, right? So I need to bring the k down, c sub k, x to the k minus 1. So I'm going to say that I want to allow for my k to start at 0 because this is x to the negative 1 power that might be needed in my solution because we are looking at a singular point here. And so this is a slight difference from when we were working with ordinary points. With ordinary points, we know that we don't deal with negative exponents for the x, but in Frobenius' theorem, we want to allow for negative exponents. Our second derivative then would look like k minus 1, x to the k minus, oops, I forgot my c, x to the k minus 2, and then again allowing for possible negative x to the negative 1 values. I'm going to start my series at 0. All right, so the differential equation looks like this. We're going to put in the y double prime and then the y prime in with 6x. So let's get to work here. 6x times the double prime. K goes from 0 to infinity of k minus 1, c sub k, x to the k minus 2, minus the y prime. That's k c sub k, x to the k minus 1, plus 6 times the y. That's the original y. And that would be c sub k, x to the k. And this differential equation is equal to 0. All right, let's do this in steps. I have an extra x out here that I can factor in and make this into k minus 1 instead of k minus 2. And now might as well bring the 6 in here. So we got 6k, k minus 1, c sub k, and then x to the k minus 1 minus, and then everything else is just rewriting. Oh, and then maybe this one I'll bring the 6 inside. And now I'm focused on the powers and trying to match this up and doing the shifting and stuff like that. So I want to match the powers, maybe have everything in terms of k. So I would add 1 to this, which means I would subtract 1 for this. And I'll do the same thing for the first one. So subtract 1 from 0, I'm going to start with negative 1. And then add 1 to the powers, or to the k's, k plus 1 times k, c sub k plus 1. And then I have x to the k, but I'm going to have x to the k for all of them. So let me just put that down here, x to the k minus the sum. K starts from negative 1 because I subtracted 1. Add 1, k plus 1 to the inside k's. And then the last one doesn't change. But at least now they all have the same powers. Now the only thing that's a problem, a little bit of an issue, is the indices here start at negative 1. So what I want to do is I want to have everything start at 0, which means when k is equal to negative 1, I want to deal with that separately. I want to take that out. So let's deal with k equals negative 1 separately here and write that out. So I'm going to get k is equal to negative 1 from 2 of these sums. So I'm going to have a 6, k is equal to negative 1. This is going to be 0, right? 0. And I guess it doesn't matter what this is going to be. No, yeah, the next one is negative 1. C sub 0, x to the negative 1. Doesn't matter because it's all going to be 0. And then the next one over here is k is also negative 1, so that's also going to be 0. So because 0 is a solution to the indicial equation, this is the reason why we're getting 0 for this. And so, but we should always expect that. Expect this to be 0. All right. Now that the negative 1 is gone, we can imagine that starting everything at 0 here. So everything else will start from 0. So I'm going to do a couple of things. I'm going to, they all have x to the k. So I'm going to put x to the k out there. The first two have c sub k plus 1, and then the last one has c sub k. So I'm going to take the first two, combine them within this parentheses, and then I'm going to take 6c to the k, or c sub k here. So these two I'll combine with c sub k plus 1 separated or factored out. So let's see, what do I have here? I have 6k squared plus 6k. Is that right for the first one? And then c sub k plus 1 factored out. For the second one, I have a negative k minus 1. Is that right? A negative sign out here and k plus 1, so negative k minus 1. And so I want to combine these two together, put that in there. So I got 6k squared plus 5k minus 1. All right. So when k is equal to negative 1, that whole thing is equal to 0. We don't need to worry about this. Now, when k is 0 and k is 1, k is 2, we're going to find a relationship between our values here. So in general, you want to take this relationship and solve for the larger c sub k value, or the larger c sub value. So I'm going to solve for c sub k plus 1, and this is all set equal to 0. So over here, we get a relationship that says c sub k plus 1 is equal to negative 6 c sub k divided by this whole thing. Okay. All right. So that'll help me find the coefficients. And so what I'm going to do is you're just going to go through k is equal to 0, k is equal to 1, 2, 3, etc. to see if we can find a pattern. Or I think this particular problem in the book is a multiple choice. So, and then these choices look like, the numbers look like they're all simplified. So let's just go with that idea that we're going to simplify our values into fractions, reduce fractions. So I'm going to take this expression, or the relation between the c sub k's, and put 0 in for k. So 0 in for k, the first one I'm going to solve for is c sub 1. That's equal to negative 6 times c sub 0 divided by, I'm going to put 0 in for k. That's just negative 1 in the bottom, right? 0, 0, minus 1. So it looks like our c sub 1 is equal to 6 c sub 0. I'm going to rewrite it like that so I can box it. Okay, let's try k is equal to 2. K is equal to 2 here. I'm sorry, k is equal to 1. K is equal to 1 here. I have c sub 1 plus 1. That's c sub 2 is equal to negative 6. C sub 1 divided by, now I have to put 1 in here. 6 plus 5, 11, minus 1 is 10. That's a negative 6 over 10. I suppose I should start reducing. Times c sub 1. C sub 1 is 6 c sub 0. The 6 is starting to look like a c sub 0. Cancel. Yeah, that's it. 5, 2, 3. 18. So c sub 2 is negative 18 over 5 times c sub 1, or c sub 0. All right, let's do one more. C sub, when k is equal to 2, I have c sub 2 plus 1 is 3. C sub 3 is equal to negative 6. C sub 2, k is equal to 2. When k is equal to 2, oh boy, 2 squared is 4, 24, plus 5 times 2 is 10, 34, minus 1, 33. 33, and that's a negative 6 over 33 times c sub 2. Now, I don't have to backtrack. I can just say c sub 2 is negative 18. Oh, boy. Fractions. So c sub 3 is equal to, can I cancel? I can cancel a 3. 11. This is 6. Negative, negative is a positive. I have 36 over 55 c sub 0. Okay. All right. I think we can hopefully stop here and maybe write down our y sub 1 solution. And if you look at y sub 1, it's supposed to be equal to k goes from 0 to infinity of c sub k x to the k. So when k is equal to 0, I start off with c sub 0 times x to the 0, which is just 1. When k is equal to 1, I have c sub 1. C sub 1 is, I'll just put 6 c sub 0. Maybe we should factor out a c sub 0. You can see that everything has a c sub 0 here, right? I'm going to go ahead and factor out a c sub 0. Sorry. So factor out a c sub 0. And so the first one is c sub 0. So that's just c sub 0 times 1 factored out. The next one is looks like it's positive, right? Positive 6 c sub 0. And c1 has an x to the first power attached to it. C sub 2 times x squared. So c sub 2 is negative 18 over 5 times c sub 0, which we factored out. And then that c sub 2 is multiplied with x squared. And we'll go one more. Next one is a positive. C sub 3 is 36 over 55 times c sub 0, which we factored out. And c sub 3 is multiplied by x cubed. And for now, let's put dot, dot, dot here. And if we need more values, we can use this relationship to find our next one. Good? All right, so that's one of them. Our next one is the one with a 7/6 attached to it. So let's do this next one on the next page. Let's see what we can do. All right, we need the first derivative. So remember, for Frobenius theorem, when you're dealing with regular singular points, your derivatives always are is going to start with k is equal to 0, right? And so we got, k plus 7/6, c sub k x2. I have to subtract 1. So this is k plus 7/6 minus 1, or minus 6/6. I think that's going to leave me with 1/6. The second derivative, again, starting with k is equal to 0, is going to be k plus 7 6 times c sub k, and then this power goes down, k plus 1 6 x to the k. Now I have to subtract 1 again, so I have 1 6 minus 1. That's negative 5 6 maybe. Okay. So now we need to put this into our differential equation. Our differential equation is this guy. So let's put that into our differential equation. I have my second derivative times 6x. K goes from 0 to infinity. K plus 7 over 6. K plus 1 over 6. C sub k, x to the k minus 5 6. So this extra x being multiplied in there will increase that power just a little bit. We'll do that in the next step. K goes from 0 to infinity. The first derivative is just k plus 7 6. C sub k, x to the k plus 1 6. And then finally we have a 6 times the original function c sub k, x to the k plus 7 over 6. All right, so the first thing I'd like to do is multiply this 6x inside here. That'll change the power, and I'll have to rewrite everything over again. K plus 7 over 6, k plus 1 over 6, c sub k. Oh, let's put the 6 in there, and then let's change this to x to the add 1. So that becomes k plus 1 6. I'm not going to write everything down here. I'm just going to say everything else will remain the same. So the other trick to this that might be good to remember is that we're going to take out an x to the 7 6 power. Okay, we can do that now, or we can do that later. Let's try to get this k plus 7 6 business going by adding 1 to the k inside, which means we have to subtract 1 here. And that's essentially what we did last time too, remember? So let's do this in a step. So let's add 1. I got 6. I got k plus 13. K plus 7 6. C sub k plus 1. X to the k plus 7 6. And what we're going to do is we're going to take out an x to the k plus 7 6 power. We'll do the same for the second one. K plus 13 6. C sub k plus 1. X to the k plus 7 6. And then the last one remains the same. Let's put the 6 in there. Yeah, I think so. Yeah, that should also work out. All right. So the thing to do is at this point, is to factor out an x to the 7/6. And then we can separate. We could do a couple of steps all at once here. We could take out an x to the 7/6. So we could be working with this thing. That's just x to the k. By taking out an x to the 7/6. So let's do that first. And then the next thing we're going to do is we're going to combine the first two. Well, before we combine the first two, we have a k is equal to -1 business that we want to get rid of. So let's get rid of that. We have a 6. Let's make sure we're getting k equals -1. The first term for the first two series. So we'll put -1 in for k. We have 6 -1 plus 13 over 6, -1 plus 7, 6, c to the 0, and then x to the -1 power, minus this thing, -1 plus 13 over 6, and again c sub 0, x to the -1. Now, this thing, when k is equal to -1, this thing should be equal to 0 when we took it out. Okay? So I hope that's equal to 0. I'm not going to work it out. I'm more concerned about what's going to happen after that. So what's going to happen after that is that we're going to get a sum. Because when k is equal to -1, we got rid of those terms. So we're going to start with k is equal to 0 of these things. Now remember, the first two are have the same c sub k plus 1 and an x to the k. So I have 6 k plus 13 over 6, k plus 7 over 6, and then c sub k, I'll factor that out later, and then I have k plus 13 over 6. So now this thing has a c sub k. It also has an x to the k, or c sub k plus 1. It also has an x to the k, but we'll put that in when we throw in this last one. So we got a plus 6 c sub k, and then now we'll end it with an x to the k power. Maybe I'll change the brackets, change these things into curly brackets. If that makes a difference. All right. So here's your relationship between c sub k plus 1 and c sub k, and then you're going to solve for it. But I guess before we solve for it, let's do some simplifying. Let's simplify this out a little bit. Can we? Is that possible? What's the best way to do this? They all have the same denominator, so let's FOIL out these two terms. I got k squared plus plus plus. You add the terms, so 13, that's 20 over 6. And then multiply them. Oh, what's 7 times 13? 1, 2, 91. 91 over 6. No, over 36, right? So multiply that times 6 and then subtract k plus 13 over 6. So let's distribute the 6. 6k squared plus 20k plus 91 over 6 minus k minus 13 over 6. So 6k squared plus 19k. 91 minus 13. 78. Does that reduce? 78 over 6? Oh yeah, it's 3 is 13, right? So 6k squared plus 19k plus 13. So that's it. We set this whole thing inside of the curly brackets equal to 0. We're going to get a relationship where we get to solve for c sub k plus 1 is equal to negative 6 c sub k divided by this whole thing that we just worked out, which is 6k squared plus 19k plus 13. That's your relationship for k. Yeah?
Do you know how you factor out the x of 7, 6?
Uh-huh.
Is that still part of?
Oh yeah, we should close this up. It's still part of that, but yeah, in terms of what we're solving for at this point, it doesn't matter. We just have to remember when we write out our final answer that there's going to be an x to the 7, 6 in front. All right. So we got k is equal to negative 1 taken care of. That's equal to 0, and that's out of there. So we got k is equal to 0, k is equal to 1, k is equal to 2, etc. So we'll use this relationship to figure out our c sub 1, c sub 2, c sub 3 in terms of c sub 0. So we got c sub 0 plus 1 is equal to negative 6. C sub 0 divided by k is equal to 0. I just got 13 there. So that's my c sub 1. C sub 2, whoops, k is equal to 2. No, k is equal to 1. I have c sub 1 plus 1, so that's c sub 2. Negative 6 c sub 1 divided by, yeah. $37? $38? And we got negative 6 over 38 times c sub 1. C sub 1 is negative 6 over 13. $38 is even at least. It's half of 38. 19? 19, 3, so it's 18. So c sub 2 is equal to positive 18 over, what's 13 times 19? To what? 247 times c sub 0. do one more. Oh, goodness. K is equal to 2. So 2 in here, we got C sub 2 plus 1 is 3 is equal to negative 6. C sub 2 divided by, 24 plus 38 is plus 13. Ah, lost it. How you guys can tell me? What is it? 75? Oh boy. So that's negative 6 over 75, and that gets multiplied by C sub 2. Oh boy. 18 divided by 247. 247 is a product of two prime numbers, and neither of them are 3 or 2, so they're not going to cancel. I don't think anything will cancel here. Oh, 3 and a 5, right? 6. This is 25. So I need some 25 times 248, or I'm sorry, 247. This is a negative. I'll put a 36 up on top. Don't forget the C sub 0. What is this? 25 times 247? $6,000? All right, let's stop. C3. Let's write down what I think the answer should be. So they all have a C sub 0. We can take that out. And remember, the other thing about this particular solution is remember that we took out an x to the 7/6. So we can write x to the 7/6, taking that out, times C sub 0 as our constant. And then now let's start writing our power series. So that's C sub 0 plus C sub 1 times x. So C sub 1 has a C sub 0 that we factored out, so we're really just concerned about this 6 over 13 negative times x. The next one is a positive, C sub 2 times x squared. C sub 2 is 18 divided by 247 times C sub 0, which we factored out. Multiply this times x squared, and then minus 36 over 6175 C sub 0, which we factored out. And this is C sub 3, so this is multiplied by x cubed. All right, let's, I don't even want to look at the answers. Let's look at the answers. Oh, 671, was that it? So so this is our first one, right? It's 1 plus 6x minus 18/5 x squared, 36 over 55, was that? Whoa. No way, look at that. I'm all shocked. And then the next one, is 7/6, x to the 7/6 taken out. We have a 1, negative 6/13, 18 over 247, negative 36 over that. Oh, we got it. Oh, so those are C sub 0 in our calculations. They were arbitrary constants that we took out. And so essentially we can change this to whatever we want, a or c sub 1 or whatever. But it's different from the c's that we solve for that's part of the series. I guess it's kind of unfortunate that we're using c's for the series. In general, I tend to use a's, like a sub 1, a sub 2, a sub 3, but they use c's, and but that's just an arbitrary constant. And it turns out that all the coefficients of the power series are all related to that one arbitrary constant. So we take that one arbitrary constant out, and then we can change it to whatever we want now. So I suppose we had our roots here as 0 and 7, 6. Let's check it. Is it right? Is it right?
That's what it feels like submitting the homework.
You hold your breath, and then if your computer's slow, you're holding your breath for a long time.
Yeah. I wonder how long one of those has to be. 5 minutes.
Yes.
Watch it, you're like 2 minutes.
Yeah.
All right. I think this is worth copying and putting in our notes because we got it right. No, I'm telling you, though, this is, remember I was talking about last, what was the last thing we did before the test? Something. Linear transformation. No, that's linear algebra. Variation of parameters. Yeah, remember that was taking like a page, maybe a page and a half. And I said, just wait till you do power series and at least 2 pages for one problem. So it turns out that the way we did it might not be the most efficient way.
What is the most efficient way?
The most efficient way, probably, I don't know if it's a shortcut, but you know how we found the indicial roots from the beginning? The way the book does it, the book doesn't find the indicial roots first. What the book does is that it assumes that your solution is of this form, and then it goes with that. Should we try to do a little bit of it? I don't want to redo the whole thing. And then get nightmares and flashbacks and stuff. So let's take a look at the original problem again and see how you would start it. Assuming that you know that you have a singular point. So without knowing your indicial roots, which is what we did first, what the book does, and I guess most other people, aside from me, what they do is they assume that your solution looks like this. C sub k goes from 0 to infinity of x to the k plus r, where you don't know what r is yet. And in the process of doing this, you'll eventually find out r by plugging in your first and second derivatives. So let's do that. Let's find the first derivative, keeping this the way it is. So again, we don't make assumptions about this series as being a power series because we have roots that are non-integer, non-positive integer. So we're going to keep this at k is equal to 0. And then I have a k plus r, c sub k, x to the k plus r minus 1. So if you're good with manipulating symbols, then this method would probably be okay with you. The way I did it, we kind of found the indicial roots first, and then we dealt with numbers instead of symbols. And the symbols I mean like k plus r minus 1 kind of business. All right, the second derivative, again going from 0 to infinity. Now I have a k plus r, and k plus r minus 1, c sub k, x to the k plus r minus 1, which is minus 2. So now you put these into your differential equation, and you get 6x times the second derivative. K goes from 0 to infinity. I'm rewriting everything over again. This is this is the way the book does it, and it may be more efficient. But I think it's more symbol heavy. So the second one is the y prime with a negative sign. So the y prime, k goes from 0 to infinity, k plus r, c sub k, x to the k plus r minus 1. And then the last one is multiplied by 6, c sub k, x to the k plus r. So we'll kind of do the same thing. We'll distribute the x, and I'm not going to rewrite everything over, so I'm just going to use a different color and say distribute the x, which means this is going to become k plus r minus 1 after I distribute the x. We throw the 6 in there as well. And the other thing we're going to do, and we'll do this in our next step, is take out an x to the r. So that's like taking out that x to the 7/6 that we did. Now when we take out an x to the r, we have an x to the k. We took out an r, x to the r, so we have a k minus 1 left. So I'll write this as k goes from 0 to infinity, the same thing right now. X to the k minus 1 minus, this has the same thing. I wonder if I should just keep it in the same, or should I rewrite that summation sign again? Because they have x to the k, and then we'll do the same thing. We took out an x to the k. So I'm going to take out the summation sign for this one. So this is all under one sum. I put these two sums together. And then the other one has a different power, so I'll keep that separate. And we took out an x to the r, so this is just x to the k. Oh yeah, the 6. All right, now to match the powers, we do that index shifting, add 1, so subtract 1, and then you'll have that 0, that k's negative 1. So we'll do the index shift. So this is add 1 to the k, so k plus 1 plus r, so I'll just k plus r plus 1, k plus r plus 1 minus 1, c sub k plus 1. Oh, I can even take out, I can factor out and c sub k plus 1, so let me move that over. So the first two summations can be simplified into something like this. I mean, we can probably even simplify this a little bit better. But this simplifies to this so far. Starting at k is equal to negative 1. And then this one still starts at k is equal to 0. So we're almost ready to combine this except for our -1 business here. So we need to separate that. So we'll rewrite k is equal to -1 separate. And we'll write the rest of them with a summation starting at k is equal to 0. So when k is equal to -1, I have a -1 plus r plus 1. So it starts off with an r. When k is equal to -1, I have an r minus 1. Right? K is equal to -1 again here. I have just an r. Is that right? So that's this business in here, c sub 0 when k is equal to -1 and x to the -1 power. And then once I get rid of that one term, then everything can start from 0. So I'll just rewrite everything over again. But this time, I'll factor out an x to the k. So I have k plus r plus 1, k plus r minus k plus r plus 1. I could probably simplify this. I think I said that already. C sub k plus 1 plus 6 c sub k, and then that whole thing is multiplied by that same x to the k power, because they're all being multiplied by that. So we're going to get a relation from here, but let's take a look at this. This is supposed to be equal to 0. Guess what this is? Let's take a look. Oh, there's supposed to be a 1/6 in there. I was going to say, that's exactly the indicial equation. Oh, I missed the 6? Where did I miss the 6? The x is right here. 6. Ah, thank you. So I lost the 6 somewhere. 6. Which x? So this becomes a 6 here, right? Oh, this x. Oh, this. Oh, yeah. Oh, that's the x you were talking about. So that 6 I missed because I tried to do this without rewriting the whole thing over with this x, and so I forgot about the 6. So I think the 6 over here. So this would make it, it's not exactly like the indicial equation, but if we solve for this, we're going to get r is equal to 0 and 7/6. So the way they do it, the indicial equation kind of pops up as you do your your series. Now, it still looks a little bit complicated, right? But the idea is that we're still wanting to solve for this thing. So I can solve for this relationship here, where c sub k plus 1 is equal to -6 c sub k divided by this big mess over here. So I'm going to rewrite everything over. Now, if we take a look at this denominator, it has a k and an r, but the r we would eventually get when we set this thing equal to 0 from the indicial equations. And when we put 0 in for r, we're going to get that relationship that we got when we set r is equal to 0 and solve that way. And when we put r is equal to 7/6, we would get that new relationship with a 7/6. So if you can keep everything kind of steady and correct, if you're meticulous enough to keep everything correct up to here, once you get this far, you take this with r is equal to 0, and then you immediately have that relationship, c sub k plus 1 is equal to minus 6 c sub k divided by r is equal to 0. I have k plus 1 times k minus k plus 1. And if you multiply this stuff out, you're going to get the polynomial that we got before. And then similarly, when r is equal to 7/6, you get c sub k plus 1 is equal to negative 6 c sub k divided by whatever that is when r is equal to 7/6. And again, you should get the polynomial that we got when we did our second one. Okay? So, I don't know if this is much of a shortcut. It does use less work. Maybe instead of 2.5 pages, it'll be more like 1 3/4 page of work. You save a little bit of time by doing. So what we essentially did when we did our work was we did this business over here where we found the relationship, and then we did our work. And then, if you notice, some of our calculations were looking pretty much the same when we did when we let r is equal to 7/6, and we did kind of like the same work. Well, the way you could do it is that you can just not use r until later, and then come up with this relationship. So it does cut your work in almost in half, but it's going to be a little shorter. Just a little. So if you want to follow through, I think example number 2 in section 6.3 in the textbook has this kind of process. All right? Okay, so on Thursday, I'm going to give you guys a take-home quiz, or I'm going to put it online. So it'll be a quiz that you can print out and then do online. But it'll cover section 6.2, which is not this section, but it's slightly easier. It's going to be 2 pages instead of 2.5 of work where you're finding a solution around an ordinary point. And so I don't know exactly what I'm going to do for the final exam yet, but I will test you somehow on your knowledge on being able to solve both ordinary and regular singular points like we just did. For the regular singular points, remember there was 3 cases. This is the first case. So we're not going to do the second case, but I do have a video of a second case. It's like 35 minutes long or something. And it's me talking at night, so talking really quietly because the kids are sleeping. Put you right to sleep. But it also is a development of a special power series function that is commonly used in a lot of physics and engineering, and that's for the Bessel function. I don't know if you guys have heard of the Bessel function before. There's a handful of functions that are defined through a differential equation and by a power series because there's no special function for it, and the Bessel function is one of them. So I'm not going to go over that. It'll be online, and I'm probably not going to test you on that on an exam. But I will test you on regular singular point case 1, where the difference between the 2 real roots and the indicial roots are not an integer, like in this case. So that means tomorrow we move on to the new chapter. And our new chapter is going to be Laplace transformations. Okay? All right. So we could be done for this. So good luck with your homework. Okay. No, I'll have it ready by Thursday when you come in, and you'll have the weekend to work on it, along with your homework. So I'll put it up sooner, but you'll have the weekend to work on it. All right, see you guys next time.